Myself. It's not recording you. All right, so this next unit is about atoms. The thing you probably expected to study a lot about in chemistry, but we weren't ready to study it yet. And we weren't ready to study it yet because we hadn't learned about how to deal with really big and really small numbers, because atoms are tiny. So we're going to need little numbers to describe them and big numbers when we count them. Okay? So we need a scientific notation. We need a way of measuring them. And scientists work in the metric system, so we had to learn that metric system. Okay? And I wanted you to get an idea of how science works, that law theory piece of the scientific method. Because that shows up here at the beginning of this unit on atoms. Because we're going to take a historical approach. We're going to see how ideas develop over time, how laws and theories develop over time, and how they interplay with each other, what the interaction's like. Now, you already have a theory. Okay? Bellwork question today. I asked you to describe that atom. That process of describing what was in your head, okay? And I'm not going to grade that on right or wrong, but I want you to go through that process, because that process right now, that picture you have in your head is your model of the atom. And an atom is just a theory. And by just a theory, I mean an atom is just the best explanation we have for everything we see. Okay? So how is an atom an explanation? Okay? That's what we're going to look at today. So we're going to start off with the history of the atom. Okay, so I don't take all period to talk about the history of the atom, so let me shorten it down for you a little bit. Okay, 14.5 billion years ago, there was a Big Bang, and the universe began. A few milliseconds later, atoms were created. That's it. That's the history of the atom. Okay. Atoms are things that exist in nature. Okay? What we're going to learn about is not the history of the atom, but the history of the idea of the atom. Where did the idea come from that the world is made up of little tiny pieces? How did they figure out that that's how the world works? So that's what we're going to study today. And we're going to start off in ancient Greece. Okay? And by ancient Greece, I mean 400 BC is the time frame. It's not even all of Greece. It's actually just Athens. Okay? And if you read about Athenian history and you learn about the famous people of Greek history, most of them were alive at this time. Okay? This is called the Golden Age. Okay? And there was a couple of Greek philosophers, one named Democritus and the other named Leucippus. Okay? Okay? They're Greek philosophers. And philosophers have the greatest job. Because philosophers, what they do is they ask themselves a question, and then they think about it for a really long time, and then they answer it after they've thought about it for a really long time, using logic and reasoning to come to the truth. It's nice you get to pick your own questions and you get to pick the answer, so you're the only one who knows if they're right. But So here's where they got their question from. Okay, they looked at a beach. Okay, and they see this huge miles and miles of beach can be made up of little tiny pieces of sand. So a beach is not really a beach. A beach is just sand. And if I dig out any part of that beach, if I take any part of that beach, I'll get sand. And if I take any sand out of that, I'll have sand. And eventually I'll get down to a place where I have just an individual grain of sand. So if I cut that little grain of sand, what would I get? Well, I'd get smaller sand. If I grind up sand, I get smaller sand. So here's the question they ask themselves. Is there a smallest piece of sand? Is there a piece of sand so small that you can't cut it and still have sand? That either you can't cut it, or if you cut it, you no longer have sand. Okay? That's the question they asked themselves. And they thought about it for a really long time. And according to the philosophy of their thinking, they said, there must be. There has to be a piece so small that you couldn't cut it anymore. And they called that smallest piece atomos. That's a Greek word. Okay, and the root word, tome, means cut or sever. The prefix a means not or without. So, not cut, without being cut. The word we would have used, instead of atomos, we would have called them indivisible. Not invisible, indivisible. There's a difference between those two. Not to be cut, not to be divided. Okay. And that's where we got our word atoms, from the word indivisible in Greek. Okay. I said this was the golden age of Greece. There was another Greek around. His name was Aristotle. Okay. Now just think about it. How many of you had heard about Democritus before you did the reading? Most people are shaking their heads, not me. How many people had heard of Aristotle? I see a lot more eye contact with that one. Oh, yeah, I've heard of Aristotle. Yeah, he's famous now. He's been famous ever since then. We'll talk about why. Okay, but first, let's talk about him and how he saw the world. He was in a different school of philosophy than Democritus and Leucippus. Democritus and Leucippus were in a group of people that thought in chunky pieces, so that the idea that there was a piece of sand made sense to them. Aristotle thought everything was on a continuum. Okay, and just like the number line, if you got two numbers, you can always find a number in between it. That there's always a smaller piece in between. So the number line is continuous. Aristotle thought the world was that way too. That there would never be a piece of sand so small that you couldn't cut it. Instead, he believed that the universe was made up of 4 elements. Now, these are not the elements the way we talk about elements as scientists now. His 4 elements were fire, air, earth, and water. Those were his 4 elements. And each element had a specific set of properties. Okay. Fire were things that were warm and things that were shiny. Air was light, and it also tended to be warm as well. Earth was cool and heavy, and water was wet and heavy. And Aristotle says all the changes we see in the world are just blending these things in different proportions. That what makes one piece different, what makes aluminum different from lead is aluminum is earth with some air in it and a little fire because it's a little bit shinier and a little bit lighter. Lead is almost pure earth. Okay. So to us, water, liquid goes to water as a gas. That's what happens when we boil water. That water turns into steam, and steam is just water as a gas. Okay? But to Aristotle, that is not what happened. Water, the element, made steam, and steam was wet, so it's got water, and it was hot, so it had fire. So Aristotle said water plus fire makes this new stuff. Water fire, which we call steam. It's not the same stuff as you started with, because you made something new. Whereas we know that the stuff that condenses on our mirror in the bathroom is the same stuff that we took the shower with. It's water. So we have two competing philosophies. Democritus and Leucippus on the side of individual chunks. Aristotle in terms of continuous pieces. Well, now, if we disagreed about science, we'd do the experiment. We'd find an experiment that differentiate between those two. But Greeks wouldn't do that. Okay, we talk about this as the golden age of Greece, but what we don't talk about real often was it was the golden age for the property owners. Okay? The people you read about in Greece were the rich and famous, because lots of slaves in ancient Greece. So the people who are doing all this thinking have lots of free time because somebody else is doing all the manual labor. And they don't think you get to the truth by experimenting. They think that truth is in logic and reasoning. And the way the logic and reasoning proved itself out was by argument. So they just went in and made arguments and debates about how the world worked. And their argument was a very formal thing called the rhetoric. It's a very structured debate. And it's what people did for entertainment. So they would have a debate in the amphitheater, in the agora, and people would come and watch it. So we already know the winner. The reason why we know the winner of this debate is because you knew one of the names before you got here. You'd heard of Aristotle, but you hadn't heard of Democritus. Aristotle won. He was a better debater. He won the argument. So Aristotle's ideas got carried on. And a few hundred years later, they got picked up by the early Christian church and wrapped up into that church's philosophy. So that his ideas carried through the Middle Ages in Europe, because everybody was tied to Aristotle's ideas. Because if you went against Aristotle, you went against the church. And if you went against the church, you didn't live long. Okay? So, people thought the world worked this way. And the people who actually experiment this way are not called chemists. They're called alchemists. You can see we get our word chemistry from here, but alchemy, okay? When I picture an alchemist, I picture Merlin in King Arthur's court. Because what he did was he makes things change, they look like magic. But they're not magic, because magic would be a sin, okay, to them, okay? So it's got to fit with Aristotle's philosophy. And one of the big things alchemists were trying to do was turn lead into gold, because it makes sense that you're able to turn lead into gold if Aristotle is right. because lead is almost pure earth. It's cool. It's one of the densest stuff. Gold is more dense than lead, so it's got lots of earth, but it's shiny and it's yellow. And the shiny and yellow implies fire. So if I can just find a way to get fire to stick to lead, I can make gold. If Aristotle's right, you should be able to turn lead into gold. They weren't crazy. They were just wrong. They weren't stupid. They were just wrong. They had the wrong system of how the world worked. Okay? But they kept it for, a little while. Say, through the Middle Ages, your book doesn't talk about it, but science really didn't get invented until the late 1500s. Okay? That's when science, the idea that you should experiment and let the world tell you about the world. That didn't happen until the late 1600s. Late 1500s, sorry, late 16th century. So who's next on our atom parade? The next person that shows up in the late 1700s, about the time of the American Revolution. His name is John Dalton. In England, he was a teacher. That's what paid the bills. But a teacher in 1700s England was not like my job, because the government hires me to teach all the children because every child gets an education. Well, that's not the way it was then. What would happen is a family or a group of families would hire a teacher, and that teacher would teach all their kids. Okay? So that's what he did. That's what he did for a day job. And for a night job, not really for a job, but for a hobby, he was looking at this new idea of elements. Because they changed the definition of element between Aristotle and Dalton. And your book doesn't talk about it happening. But they changed the definition. It's no longer fire, earth, and water. Okay? They said, okay, element like in elementary, as in basic, the smallest piece. So they said an element was something that couldn't be broken down anymore. That the only way it could change would be to have pieces added to it and be heavier. So what they would do to find an element, they would take something that they didn't know what it was made up of. Hey, this might be an element. Let me try to tear it into pieces. And if they could tear it into pieces, they knew it wasn't an element. And if they knew what either of the pieces were, that was uninteresting to them. It wasn't a new element. They threw it away. But if they got a piece they didn't know what it was, they tried to tear that apart. And if they could tear it apart, they looked at the pieces. The ones they knew, they threw away. The ones they didn't know, they tried to tear apart. And eventually they got to something that they couldn't change by making into smaller pieces. That was as simple as it could be made. So that was the definition of element that Dalton was working on. Okay? It went away from fire, earth, water, that. So that's a new definition of element. Okay? So he's got that to work with. And he noticed some patterns of behavior. We call patterns of behavior laws. So now we're going back to the scientific method piece of this. Okay, the scientific method got invented in the late 16th century, late 18th century. We're coming up with these ideas. And the reason why we're able to come up with these ideas is because Dalton didn't have to do all the experiments. By the late 1700s, Europe had a good enough postal service that you could ship magazines, books, and letters across Europe. That you could give a letter to somebody in London, and you could expect it to be delivered to Italy. It might take a couple of months, because it could never move faster than a horse. but you could expect it to get there and expect a response in a few months. And so you could share data that way. And that's what he was looking at. He was looking at other people's data from the experiments of tearing stuff into pieces. And one of the things they noticed was the conservation of mass. Okay. Well, the primary laws of science, conservation of mass, conserve means to save. So the law of conservation of mass is that mass is saved. And scientists always tend to understate. So when they say conserve, they mean every single piece is saved. That if you weigh all the stuff at the beginning and you weigh all the stuff at the end, those two weights are going to be the same, no matter what change you do. It took them a long time to come up with this idea because it's really easy to come up with examples where it doesn't hold true. I take a piece of wood. I weigh it. Then I burn it. Are the ashes going to weigh the same as the wood? The ashes are much lighter than the wood. So if the ashes are lighter than the wood, that looks like mass got destroyed. But that's not what happened. Because we weren't counting everything. First of all, wood doesn't burn without oxygen. Excuse me. Wood doesn't burn without oxygen. So I really have to count wood plus oxygen. And burning doesn't just make ash. It also makes smoke. It makes carbon dioxide. It makes water. So what they found was equal was wood plus oxygen equals ash plus smoke plus carbon dioxide plus water. Those are the two pieces that were equal. Everything at the beginning equals everything at the end. You got to count everything. And to prove it, they did stuff like this. They took a little piece of wood and they put it into a container that was sealed tight, airtight. And they put that whole container on a balance and weighed it. Now the container was actually made of glass so they could see the wood on the inside. Then they took a magnifying glass and used the sunlight to light the wood inside the thing on fire. So stuff inside burned. But while it was burning, the balance never moved. When it was done burning, the balance still didn't move. Because all the mass was still inside that container. The container, everything was still there, so all the mass was still there. So that was their proof that mass was conserved. Okay? It's one of their many proofs, but that's the one that breaks the one that we see most often. Fire seems to destroy stuff. Why didn't it? Okay? Dalton wasn't responsible for this one, but he had to explain it. Then there was the law of definite proportion. Compounds have a constant composition by mass. So the word definite means unchanging, certain. Those are synonyms for definite. Proportion is ratio. So it's the law of unchanging ratio. It's the law of certain ratio. And that ratio is the ratio of how they react, a specific ratio by mass. For example, water. Water, if you tear it apart, the oxygen in water will always be 8 times heavier than the hydrogen. It doesn't matter how much water you have. It doesn't matter where you got the water. If you take water and tear it apart, the oxygen will be 8 times heavier than the hydrogen, every time. It's a certain ratio. If you've got that ratio, it could be water. If you don't have that ratio, it's not water. Okay. Then there's the law of multiple proportions. I'll let you copy this down because it's a mouthful and I need to explain it because I would have written it shorter if I could. Okay, so it's the law of multiple proportions. When 2 elements form more than one compound, the ratios of the second element that combine with 1 gram of the first can be reduced to small whole numbers. Whew. Okay, so let's tear this apart. When 2 elements form more than one compound, so that means a compound, there's one compound made up of carbon and oxygen, there's a different compound made up of carbon and oxygen. 2 different compounds, or 3 or 4, as long as they're just carbon and oxygen. The second one is tough to understand because it's got 3 prepositional phrases. So I'm going to get rid of those. We'll get rid of everything that starts with the prepositional phrase. So if I get rid of those prepositional phrases, the ratios can be reduced to small whole numbers. Okay, so the ratios can be, that's the main idea, that ratios can be reduced to small whole numbers. What ratios? Well, that's what all the parenthetical stuff is, the prepositional stuff is about. Okay, the masses of the second element that combine with 1 gram of the first. So the first element, it's going to be so many grams of carbon for 1 gram of oxygen. The next compound, it's going to be so many grams of carbon for 1 gram of oxygen. Each one's going to have its own ratio. A different ratio because they're different compounds. If I take a ratio of those ratios, then I'll get a small whole number. The ratio of the ratios is a whole number ratio. The ratio of the ratios is the whole number ratio. But when people first see this, this is what goes through their head. What? Okay, so I already mentioned this. Water is 8 grams of oxygen for every gram of hydrogen. Okay. There's a second compound that is just hydrogen and oxygen. Hydrogen peroxide has 16 grams of oxygen for every gram of hydrogen. So the first ratio is 8 grams of oxygen for every gram of hydrogen. The second one is 16 grams of oxygen for every gram of hydrogen. So those are my ratios. Now I want a ratio of those ratios. So if I take that 16 and divide it by 8, I get 2. It's a 2-to-1 ratio. That is a whole number ratio. 2 to 1 is a whole number ratio. So, first parenthetical phrase, or first phrase, when 2 elements form more than one compound. That's this, water and hydrogen peroxide. The ratios are small whole numbers. We got that part. What ratios? This is the first ratio in the first compound, ratio in the second compound. So the ratio of these ratios is a whole number ratio. The ratio of the ratios is a whole number ratio. That shortens it. Okay, so Dalton came up with definite proportion and multiple proportion. Other people came up with the law of conservation of mass, but Dalton knew about it because he could get mail and read books. Okay. So Dalton wanted to explain those laws. Why do I always have the same ratio in the same compound? Why, if I have two compounds, is the ratio of the ratios a whole number? What would explain that happening? So how did he explain those laws? Well, he took the idea of elements, the idea of simplest matter, and combined it with the idea of atoms, smallest pieces. And he came up with an explanation. And our name for that explanation is Dalton's atomic theory. Familiar word there? Theory? Theory about why things happen the way they do. Dalton was answering a why question when he came up with the idea of atoms. Why is there a definite proportion? Why is there multiple proportion? And he says the answer is atoms. Here's the parts of his theory. Okay. All matter, that means stuff, anything, is made up of tiny, not invisible, indivisible particles called atoms. Okay. All right, so let's get to the right spot. There we go. Okay, indivisible. That's atomos, not to be cut. So everything's made up of little tiny pieces called atoms. And then he immediately tied the idea of atoms to explain elements. Okay? He used atoms to explain elements. He said, the reason why there's simplest kinds of matter is if you've got the same element, it's one kind of atom. And if you've got a different element, it's a different kind of atom. Every atom of each element is identical, but they're different from the atoms of other elements. Now, the only thing he knew they were different about was weight. He could tell you which atom was heavier. So atoms of one element are identical, different elements different. So that's why there's the simplest kind of matter. Because if I take an element and try to break it down, I'm just getting two piles of the same kinds of atoms. I can't get, even if I break it down into an individual atom, I still got the same element. Okay? So that explains why there's elements, but elements are a tiny number of things there are in the world. I mean, now we're up to 120, but there's more than 120 different kinds of stuff in the world. Where's all the other stuff come from? Well, the other stuff is compounds. And compounds are put together by putting together atoms. So this part is explaining why there's different types of material in the world. That to make water, you put together hydrogen atoms and oxygen atoms. There is no water atom, there's a water molecule. And then he came through and said, this is what's happening in a chemical reaction. What happens is the atoms are rearranged. I don't make any new atoms. I don't destroy any old atoms. The atoms I have are just rearranged. What number 4 is explaining Number 4 explains the conservation of mass. Conservation of mass. Mass can't be created or destroyed. All the mass I start with, I have to end with. Why is that true? Well, it's true because atoms can't be created or destroyed. Every atom I start with, I have to end with. So the reason mass is conserved is because atoms exist. I'm not making new stuff, I'm just rearranging the old pieces, so I'm not going to change the weight. There it is. There. Oops, so I've got a couple things I want to show you. Just got to share it with you. It's always fun trying to find the right spot. Share. I was at the right spot before, now it's gone again. Where was it? Oh, there it is. Okay, just a couple of quick videos. They're not long. Okay, so we've got a flask with a test tube inside of it, and it weighs 158.2 grams. So he's got those two liquids. So by turning it over, he lets the two liquids hit each other, and you get a chemical reaction. Something changed there. You made a new kind of matter. But still weighs 158.2 grams. Okay? And this is the explanation.
The law of conservation of mass states that in a chemical change, matter is neither created nor destroyed. It is only rearranged. For example, let's place 5 zinc and 5 sulfur atoms onto the two sides of a pan balance. The two sides balance because the contents of each pan are identical. Consider the reaction of zinc with sulfur atoms on one side of the balance to form zinc sulfide. 5 zinc atoms will react with 5 sulfur atoms with a tremendous release of energy to form 5 zinc sulfide molecules. The two sides still exactly balance. The total number of zinc and sulfur atoms on each side are still identical, demonstrating the law of conservation of mass.
Well, you know what? He said demonstrating. I think he's wrong. It's not demonstrating. It's explaining. Those pictures explained why mass is conserved. Those pictures of atoms were an explanation for what happened. The weight stayed the same. So the weight staying the same was the law. The atoms were the explanation, the theory. Atoms are a theory. They explain what's going on. I got to find the right place again. Okay, so that's how Dalton's theory explains the law of conservation of mass. Okay. What about the other ones? Okay. The law of definite proportion. Earlier, we wrote this. Each compound has a specific ratio of elements, a ratio by mass. And the example I gave that water is always 8 grams of oxygen for each gram of hydrogen. This is what happens. Dalton noticed this pattern. Why? So notice, Dalton had a law, a pattern of behavior. He didn't have an explanation yet. So that's usually what happens. Laws come before theories. What happens versus why it happens. So why does it happen? Well, because I got to put atoms together. And the atoms have to be, every atom of the same element has to be the same. So if I'm putting the same numbers of the same kinds of pieces together, I'm always going to get the same ratio. Because I'm making the same kinds of atoms have to be put together in the same numbers to make those pieces. I had to put together 1 zinc and 1 sulfur. Okay. Maybe I'll try to give you a different example. Let's say we have element A and element B. And an atom of A, weighs 3 grams, and an atom of B weighs 2 grams. Well, they don't have to be atoms, they got to be pieces. A piece of A, a piece of B. So there is compound AB2. That would be 1A and 2 Bs. And in that, the A, 1A is 3 grams, and 2 Bs would be 4 grams. So the ratio of B to A is 4:3. Okay. What if I had 5 of those? If I had 5 AB2s, I'd have 5 A's. And 5 A's would weigh 15 grams. And I'd have 10 B's. 10 B's would be 20 grams. The ratio of B to A is 20 to 15, which I can simplify to 4/3. Because all I really did was multiply the top and the bottom both by 5. Because I had 5 atoms, or 5 molecules. So no matter what number I pick here, way down here, I'm going to get that same ratio. If I pick 10 million, well, I'd have 10 million A's and 20 million B's. And down at the end, it is simplified to 4/3 every time. Because this ratio is about B to A as individual atoms. That's the ratio of 2 B's to 1A. 2 B's to 1A. And I'm always going to have that. So atoms explain the law of definite proportion. Okay? They tell you why we get definite proportions. A theory, atoms are a theory. So that's how we do the law of definite proportions. So Dalton could explain the law of definite proportions using atoms. And actually, the one that gave it away that it had to be whole pieces was the law of multiple proportions. That's where we said the ratio of the ratios is a whole number ratio. Because what has to be different about the compound is I have to add a whole number piece. So my weight is not going to be everything from here to here because I've got this piece and this piece, so my weight is going to jump by the pieces I add, which is going to give me a ratio of the ratios is always going to give me a whole number ratio. That pieces were the only explanation that explained the whole number ratio. It's a little hard to picture that, so let me see if I can clarify it with a couple examples. Okay, we said that water was 8-1, and hydrogen peroxide was 16-1. So the ratio of those was 16 divided by 8 is 2-1. Well, that was two times the oxygen, because these were numbers for oxygen, right? Grams of oxygen, grams of oxygen. So this top is twice the oxygen in the first compound. Well, if water is H2O, how could you have twice as much oxygen in the second compound? Well, the only way to have twice as much oxygen is to have H2O2. I have to go and add a whole atom, so my weight has to jump. Well, let's try it with A and B again. We got A is what, 3 grams? And B is 2 grams? Okay, so I got compound 1 is AB. AB is going to be 2 grams of B for every 3 grams of A. It doesn't matter which one you put on top. I could have AB2. And that would be, well, if I got 2 B's, that's 4 grams of B divided by 3 grams of A, sorry. It's A, not O. So this is 0.667, and this is 1.33. So those are my ratios. So if I take a ratio, 1.33 divided by 0.667, I get 2-1. And I will never be able to get a number in between these two because I can't add half an atom. So if I go to AB3, I'm going to get another big jump. I'll have 6 grams of B divided by 3 grams of A. That's 2-1. So if I do my B to A, so if I compare these two, 2 divided by 0.667 is 3-1. So this stuff has 3 times as much B as that stuff. So do you see how atoms force you to get whole number ratios? That atoms explain the whole number ratios that Dalton saw. So Dalton figured out there were atoms just by looking at tables of data that he got from, and actually, he's really glad there was good mail, because when you look at the data from his experiments, he was not a good experimenter. His data was awful. But the data he got from other people was good. And he could use that data to notice the pattern. Okay. So what kind of pattern are we talking about? What kind of problem? It's this kind of problem. Mercury has two oxides. One is 96.2% mercury by mass. The other is 92.6%. First, show that they follow the law of multiple proportions. That means I need to find that the ratio of the ratios is a whole number ratio. And then I want to speculate on the formula of the two oxides. So I want to figure out what would the formulas for these compounds be like. Okay. So 96.2% mercury, 92.6% mercury. Two compounds. Most of them are mostly mercury. All right. So let's see what that looks like. So I had compound number 1 was 96.2%. And the symbol for mercury is Hg. I'm too lazy. Compound 2 was 92.6% mercury. So in 100 grams, 96.2% would be mercury, so I'd have 96.2 grams of mercury. And the rest would be oxygen, so that's 3.8 grams of oxygen. So I'm finding the ratio in the first compound. And I push buttons on my calculator. 96.2 divided by 3.8 is 25. Okay. Now I have to do the same thing for the other one. So in 100 grams, 92.6 grams of mercury, because 92.6% is mercury, divided by 7.4 grams of oxygen. I'm getting these numbers by subtracting from 100. So if it weighs 100 grams and 92.6 is mercury and the rest is oxygen, the oxygen is going to weigh 7.4. And I push those buttons on my calculator, and I get 12.5. So there's my ratios. Now I take a ratio of those ratios. 25 over 12.5 is 2 to 1. This right here is showing that it followed the law of multiple proportions. Every time you do that with two compounds that have the same elements, you'll end up with a whole number ratio at that point. Okay. So that was the first half of the question. Show that they follow the law of multiple proportions. The second part. Speculate on the formulas. Compound 1, compound 2. So this says 2 to 1. That's twice as much, and the number on top was mercury, right? And the first one had twice as much mercury as the second one. There, now it has twice as much mercury. the mercury in here would weigh twice what the mercury in here weighs. But that's not the only possibility. Because we're not sure that compound A or that this one was 1. What if this one's 1? Well, if this has twice as much mercury, it has half as much oxygen. Does that make sense? If it has twice as much mercury, it has half as much oxygen. So if it has half as much oxygen, I put the 2 there. So the 2 probable possibilities are those 2. And we can't tell the difference between those 2 without further information. Because the first one has twice as much mercury, but the second one's got twice as much oxygen, which gives us half as much mercury. So we're in the same spot. So, make sure it's all there. That is where I wanted to stop. So, if you go to your module, you will notice that Unit 1, science is what scientists do. That's got everything we've done along the way. And we're done with Unit 1 unless you're coming to take the makeup test, the retake. Yeah. So in Unit 2, you did the reading guide. You did the bell work today. And I need you to do Chapter 3, homework number 1, which comes right out of your textbook. But I need you to be careful. On page 69, just answer 1, 2, and 3. Read the question. It's pretty straightforward. But I've given this assignment before, and people answer number 1 on 87 wrong. Number 1 on 87 does not say, tell me what the law is. It says, to explain. Yes, Adam. Okay, so the reason why is because I used whole numbers. Okay, I used counted numbers. And we get down to sig figs, it gets a little bit messy. So if I'd put 0.0 over those, you would have been happy with it, right? It was just a matter of convenience. If you do it with sig figs, there. And oh, you mean on the one I just divided? Yeah, okay. So that's why I kept the 3 sig figs, was because I defined things with that way. If you do it the other way without the sig figs, if you divide 25 by 12, you'll get 2 point something. But with 2 sig figs, it'll still be just 2. Okay. Now, it's not going to be perfect. We're going to have unsure answers at the end. So that's one of the things that makes science different than math, is math always works out perfectly. Okay. But that's what I've got for you today, so I'd like you to start those. Anybody have any questions for me? Comments? Hey, everybody thinking about the retake for those of you who took the test. I'll look at during lunchtime to see what I can do about opening up possible answers.
What's the highest score you can get on the retake?
I don't limit it. And it won't hurt you.
What? Sorry, what?
I won't limit it. To me,
Okay.
To me, proving you know it is good enough. And I'm not going to give you this option all the time. So you can't count on this.
Yeah.
Okay, so, because you guys didn't know what my tests were going to look like. I'm trying to be fair. Okay? So, and I'll try to see if I can share that test with you with the answers along the way too.
Mr. Green, do we leave?
I need you to stay with me in case somebody's got some questions, and that last they may ask.
Oh, because I didn't hear anything.
Yeah.
I didn't.
Oh, no,
it was silent, so I didn't know anything.
just go ahead and start that homework. Look ahead, see if you're going to have any questions about it, that kind of stuff.